Question 7 is about a golfer hitting a golf ball and working out how far it goes. I looked this data up. Golfers hit the ball at 17 degrees, apparently, with the driver. Presumably that's some combination of the ball bouncing after it lands and I imagine something to do with air resistance. We're going to assume the air resistance is 0, and actually our question is about how far the ball travels before it hits the floor. So in reality, it's a projectile question. We need to start off by resolving our vector. We've got two components, a horizontal component and a vertical component. This angle in here is 17 degrees. So our two components are 94 cos 17 and 94 sine 17. If you calculate their values now, that's fine. It's probably better to try and do all the calculating at the end. So to answer a projectile question like this, the first thing we're going to do is look in the vertical direction. We know that the vertical motion is independent of the horizontal motion. In the vertical direction, it starts traveling up at 94 sine 17 meters per second. It's in the upwards direction, so we'll leave it as positive. But is accelerated downwards at 9.81 meters per second squared until its displacement is 0. We want to find the time that it takes to hit the floor. Once we have that time, we can use it to find out how far it will go, because we know it travels horizontally at 94 cos 17 meters per second the whole time. So to solve this, we're going to use our favorite Suvat equation, S equals ut plus half at squared. In this particular case, whenever we get S is equal to 0, one of the things we can do very early on is cancel out one of our t's. So if I write in my 0 is equal to ut plus half at squared, then I can divide through by t, because 0 divided by t is still 0. This is because one of my solutions is t is equal to 0. It's the point at the start. Its initial displacement is 0, so it's an uninteresting result. So rearranging this equation, we want to find t, so we're going to put the u on the other side, multiplied by 2 and divided by a. So t is equal to 2u, in fact minus 2u over a. The negative sign is going to go because a is minus 9.81, whereas u is positive, so this is 2 times 94 sine 17 over 9.81, which gives us the time that the ball is going to be in the air for. That is 5.6 seconds. So quite a long time. I suppose that is really, I mean, it's traveling up at a decent speed, isn't it, at the start, traveling up at about 50 meters per second at the start. So that makes sense. So then we're going to look in the horizontal direction. Let's do that in black. In the horizontal direction, it's a much simpler setup. The time it's in the air for is 5.6 seconds, and it travels at a constant speed of 94 cos 17 meters per second. That's because the acceleration is equal to 0 in the horizontal direction. So we can just use S equals ut. There's no need for the half at squared term. So just 94 cos 17 times 5.6 seconds. This is a distance of 503 meters. Now, as I said at the start, I think it's probably reasonable to say air resistance plays an important factor. No golfer can drive the ball 500 meters, so it seems almost certain that air resistance is going to be important. In the second part, part B, so we've changed our setup now so that rather than playing on level ground, they're playing off a cliff that's 20 meters higher than the flat golf course. So I think at this point it's probably helpful to have a diagram. Golfers here, golf ball now goes along a path like this. We actually know, although we're not necessarily going to use it when we answer this question, that this distance here is just about 500 meters, just over 500 meters. In fact, you can see it traveled some additional distance because of the further 20 meters it's going to fall down. So the first thing we can say is lots of what we did in the first part of the question still holds true. We still have an initial velocity in the horizontal direction, which is equal to 94 cos 17, and an initial vertical velocity of 94 sine 17. But now, when we look in the vertical direction to work out how long it takes the ball to come up and down and hit the floor just in that direction, we have the extra complication that S, the final displacement, is minus 20 meters. So the trick that we used up here, where U was 0 and being able to cancel T, we're not going to be able to do this round. Let's have a look. We know the acceleration is minus 9.81, and we know the initial speed in this direction is 94 sine 17. So when we go to find T, I'm going to make some more space to work. We say S is equal to UT plus a half AT squared. Because of the way U is written, we're going to end up with something a little bit messy looking. We're going to end up with a quadratic in T that we then need to solve. So let's put our numbers in and do a little bit of rearranging. Really important to be careful with signs here, or it's easy to make a mistake. Minus 20 is the value of S. This is equal to 94 sine 17 times T plus a half of minus 9.81. Let's put that in a bracket so we don't think it's take away, times T squared. So to rewrite this as a quadratic in T, we're going to say 0. So because I've got my negative term in T squared on this side, I want my factor in T squared to be positive. So I'm going to write the 0 on this side. But in fact, what I'm doing in my head is putting the 0 on this side and moving all these terms across to the other side. So when I was at school, I was taught to always have the 0 on the left. I don't know if that's still a thing. Anyway, so when I come to write this, I'm going to write this as positive 9.81 over 2 T squared. Then my term in T was positive here, but when I move it onto the other side, it will become negative. So this is going to be minus 94 sine 17 lots of T. And my 20, which was initially negative when it was on that side, is actually going to stay on this side, isn't it? Because I'm moving all the terms over to this side. So this is still minus 20. So I'm just going to double check my working quickly in my head. I think I've kept track of everything here. So obviously there's various different ways to solve a quadratic. I'm going to use the quadratic equation. So I get that T is negative B, so that's 94 sine 17 plus or minus the square root of B squared, 94 sine 17 squared. Worth being careful when you put this into your calculator. If you just have the sine 17 squared, it will only square the sine function. It won't square the 94 as well. And then when I check the 4AC, so C is negative. So we're going to end up with a plus in here. So we will certainly get something that has real solutions, which is good. In fact, I think if you do it, 4AC is going to be smaller than that anyway. But anyway, it's positive, so it doesn't matter. So 4 times 9.81 over 2 times 20. So I should have put minus 20 and a minus there, shouldn't I? But I've cancelled out the negative signs already. And all of this has to be over 2a. So 2a is 9.81. Now this I've calculated ahead of time. So when you do this calculation, it comes out as 6.25 seconds. So we're going to round it. Let me just go back through my calculator and check. It is 6.25. So we're going to round it to 6.3 seconds. So there, everything in green was to do with the vertical direction. I found it takes 6.3 seconds to reach the floor. So I'm going to come in this gap I've left and do everything in the vertical direction here. Again, the vertical direction is simple because there's no acceleration in that direction. So it has a initial speed that's equal to its final speed, that is 94 cos 17, and it travels for a time now of 6.3 seconds. So I can do S is equal to UT, which is 94 cos 17 times 6.3, gives me a distance of 566 meters again. So we're going to round it to 570, far further than any golfer in real life, I think, could hit it off a cliff that big. Last part C. What happens if you're playing up a hill of gradient 5 degrees? Now, I think when you first look at this one, it's tempting to think this is going to be much harder than what we did previously, but actually it's not. I think the best way to picture solving this problem is to imagine that the whole thing is happening on a set of axes, where in this direction, we're going to plot the displacement of the ball in what I'm going to call the y direction, and this graph, the displacement of the ball in the x direction. So on my graph, I know that the golf ball is going to follow a curve. Now I'm going to exaggerate the height of the curve, but a curve something like this. We know it's symmetrical. This angle should only be 17, but there's a line that it follows. We're also now going to have a second line on my graph like this, where this angle here is 5 degrees. That's the slope. And what I'm interested in finding is this point where the two intersect. So there's two parts to this problem. We could have a look at the line to begin with, the straight line. So we know all straight lines have a formula of y equals mx plus c, where m is the gradient and c is the y-intercept. Well, y-intercept's easy to deal with. We can see that c is equal to 0. For the gradient, we know the gradient is normally written as the change in y over the change in x. If we were imagining this as a bit of trigonometry triangles, though, we could say that the change in y over the change in x is the same as the tan of 5, because tan is opposite over adjacent. So the gradient m, which should be equal to the change in y over the change in x, is just equal to the tan of 5. So the equation of my line is actually that y is equal to tan 5 times x. So remember, when we write this down, we're relating every possible y coordinate to every possible x coordinate. This will tell us how the two are related. So if we're able to write expressions for the x position and the y position, we should be able to use these to solve where the two coincide. So let's next have a look at the flight of the ball that we've got here. So once again, we'll deal with the vertical direction to start off with. We're interested in getting an expression for the displacement in the y direction. That's what we want to know. The quantities that we know are that a is minus 9.81 meters per second squared, that the initial speed is equal to 94 sine 17. But that's all we know. So we don't know the time at which it reaches the line. Now, this initially looks like it's going to be a bit of a problem, but it turns out it's not. So I can write my equation. S is equal to ut plus a half at squared, and I can say that sy is equal to 94 sine 17 times t. Because this is minus, I'm going to say minus 9.81 over 2 t squared. So here's an expression for the displacement in this direction as a function of time. That makes sense. At different times, it will have different heights, and this function describes it. Next, in the horizontal direction, this is the displacement in x. This time, the displacement in x again is much simpler because the acceleration is equal to 0. There is an initial speed which is equal to the final speed, which is 94 cos 17 meters per second. So the displacement is just u times t. So therefore sx, the displacement in the x direction, pardon me, is equal to 94 cos 17 times t. So we've now got an expression for its displacement in the y direction and its displacement in the x direction. But we know when it hits this line, get rid of that, go away. When it hits this line, the displacement in the y direction must be equal to tan 5 times the displacement in the x direction. So we can put these three equations together. We're going to substitute in our values of the displacement in the y direction and the displacement in the x direction to this equation. I think I need to make myself some more room again. So well, we got y equals tan 5 times x. Let's write that one again. Y equals tan 5 times x. So that is 94 sine 17 t minus 9.81 over 2 t squared. So that's my y term from here is equal to the tan of 5 multiplied by my x term from here. That's 94 cos 17 times t. Now it looks a bit horrendous when we first look at it, but we might notice again there's only terms in t and t squared. So actually solving this is much simpler than our last one was. We can divide by t to get ourselves started, and then we should just be able to write an expression in t. So from this, I think we should be able to say that t is equal to the square root. No, not the square root, because I cancelled it out, didn't I? So I've just made a mistake in my previous working. I think we can solve that. So we should end up, let's do it properly. We're going to bring the t onto this side and bring everything else onto the other side, but then swap everything back over. So my terms, that's going to stay on this side. So 94 sine 17. This term's going to become negative when I move it onto the other side. So that's the tan of 5 multiplied by 94 cos 17. The t is cancelled out. So that is what 9.8. So then I need to multiply all this by 2 and divide it by 9.81. So this gives me my time of flight. Horrendous thing to type into your calculator, isn't it? Sorry. I'm still going. We want 2 times all of that divided by 9.81. I've not closed all my brackets. Made a mistake. No, that's not the right mistake. Something there. Type it all in again, pardon me. So let's do it in a few shorter phrases. So let's start with tan 5 multiplied by 94 cos 17. We're going to do 94 sine 17. Take away that answer. We're going to multiply that by 2 and then divide by 9.81. There we are. That gives me a time of 3.999. It's 4 seconds to two significant figures. It's 4 seconds to more significant figures as well, bizarrely. So then our last part was how far had it gone? The question was calculate the distance a ball will travel before hitting the floor. So the range of the ball. So there's various different ways we could define this. We could define it as this distance up the slope, or we could define it as this distance along the floor. I'm going to take it as this distance along the floor, partly because it's easier to get to. So we can say S is equal to UT, which in this particular case, we're back to it traveling horizontally at 94 cos 17 meters per second for 4 seconds, which gives us our final answer. Oh, no, let's not make a mistake now, of 359.5 meters. We're going to round it to 360 meters.